Hello, grade 10s. So I am re-recording this because I noticed that when I recorded it the first time, I did not have the microphone on, so there was no audio to go with the explanation of this handout. So I'm just going to re-record quickly and then upload to YouTube so you can watch this if you wish to review throughout the semester. So our first lesson that we did together was looking at grade 9 review, and we were specifically looking at order of operations as well as working with exponents and exponent laws. So first, with order of operations, we commonly know this as the acronym that is BEDMAS. You've seen it, I think, starting in grade 6, so in early elementary school, and you continuously use it all the way through into middle school, and then you used it in grade 9 and even here in grade 10. So if you need a reminder of what BEDMAS stands for, the B stands for brackets. That is the first thing that you have to tackle if it's in your expression and you work from the inside out. E stands for exponents, which is the little power at the top of a number. And then D and M stand for division and multiplication. This is where some people get tripped up, I think, with BEDMAS rules, because we always think that because D comes first in the acronym, we have to do division first. When really, multiplication and division are considered of equal precedence, meaning you're going to do whichever one comes first. So if you have multiplication happening first in your expression, we will do that before division. A and S are addition and subtraction, and again, they are of equal precedence, meaning whichever one is happening first, you will do. So it doesn't necessarily always have to be A, because it comes first in the acronym. It's whichever one we see is happening first when we work left to right. So for example, with example 1, we're asked to calculate the value of that whole expression, which, okay, I'm looking here and I am seeing brackets. So if I use like BEDMAS as a checklist and I'm starting with B, I say I have brackets, I need to tackle these brackets first, right? So I'm going to say over here, my first bit of the expression is going to stay the same. So 2 to the power of 3 minus 3 times, and now I need to simplify my brackets, which you'll see the square brackets and the round brackets are two different sets of brackets. So it's like I've got brackets and brackets. So really, I gotta look at this first before I can simplify all that other stuff. So I'm gonna leave the 5 for now, and I'm gonna simplify what is negative 14 plus 12, which if I simplify that, that should leave me with negative 2. And notice I kept that answer also in brackets, because you'll see that when we go to subtract a negative, it's going to turn into a positive. So okay, I'm going to continue. I'm going to say that this is equal to 2 to the power of 3 minus 3 times. And now I can simplify this bracket now that the other bracket was solved. So I'm left with 5 minus negative 2, which is like saying 5 plus 2, which will leave me with 7. Now I have to go through, okay, my B is done, my brackets, I've just got that 7 there, which is multiplication. If I move on to E, which is exponents, I see that I do have an exponent. It's attached to this 2, so I have to evaluate that first before I can do any of the other multiplication and subtraction. So if I do 2 to the power of 3, this is not the same as 2 times 3. So a lot of people will see this and they'll say that it's 6, but that is not true. The power just means that's how many times you're going to multiply 2 by itself. So this is really like 2 times 2 times 2, which will be 8. So we're left with 8 minus 3 times 7. I don't have to keep writing the brackets for 7. It's fine. It's just 7. So okay, exponent is done. I'm moving on to the next letter. D, I don't have any division, but I do have M, multiplication. So I'm going to do that first before the subtraction. So this is really going to be 8 minus 3 times 7 is 21. And then my last step is the subtraction. So I can subtract those two terms together, and it will be negative 13. And that is your expression. If you were to go out of order of BEDMAS, you would notice that your answer will be way different. So for example, if I had subtracted in this bottom third line and did 8 minus 3 first, then I would be doing 5 times 7, which is positive 35, way off from negative 13. So that's why it's important to kind of use BEDMAS as like your checklist to ensure that you are following the correct order. Okay, moving on to the second one we've got here. This one we felt a little scared of in class, I think, because of the fractions within fractions and having so much stacked on top of each other. But we just approached this by, can we simplify the top first? Can we simplify the bottom? And then we'll divide them. So we got to make this look a little prettier, just so it makes a little bit more sense. So, okay, if we did the top first, we said that this is just negative 6 over 7 times 1 over 2 plus 1 over 3, which when I am adding and subtracting fractions, we need a common denominator. So the bottoms have to be the same anytime you're adding or subtracting. So in this case, I'm looking at 2 and 3. I'm thinking, what could their lowest common denominator be? Which I think it is 6, because I can times 2 by 3 to make 6, and I can times 3 by 2 to make 6. So what I do to the bottom, I have to do to the top as well. So if I'm timesing this by 3, I'm also timesing the top by 3. Same thing for the second fraction. If I am timesing this by 2, I also have to times the top by 2. And you will see that this will leave us with still negative 6 over 7 on the outside, but now I'm going to have 3 over 6 plus 2 over 6. Which, now that the bottoms are the same, they're both 6, now I can add the numerators. So this is really going to be negative 6 over 7 times 5 over 6. Now, I said for multiplication of fractions, you do not need a common denominator. We don't have to worry about making the 7 and the 6 the same. That is only when you're adding and subtracting. So in this case, when you are multiplying, you are just doing top times top and bottom times bottom. You can also use a fast trick that I don't think I mentioned in class, just because I wanted you to see kind of how we got these numbers. But if you ever have a repeating number that's in the numerator and denominator, you can just cancel it out. So for example, we both got 6's here. I can cancel out the 6's. And my final answer will just be negative 5 over 7. Easier, right? If I had not known to do that, for example, and I just did do it the long way, and I said, okay, negative 6 times 5 and 7 times 6, and I just multiplied top with top, bottom with bottom, I would have gotten negative 30 over 42, but a lot of your calculators would have simplified this anyway, and it would have simplified to negative 5 over 7 if we're dividing both the top and bottom by 6. So either way, you'll get the same answer. The other way is just a faster way of doing it. So, okay, all of that work was just for simplifying the numerator. We're going to do the exact same thing with the denominator. So, okay, on this line, I'm going to go here in purple, and I'm going to rewrite my expression. So I've got 2 over 3 minus, when we have a whole number, we're just going to write it as over 1 since it's not a fraction, so it doesn't have a denominator. But you'll see when I'm adding also 7 plus 2, I've got 3 things that I'm adding and subtracting together. The rule with fractions is if I'm adding or subtracting, I need a common denominator. So I have to look between 3, 1, and 2. What's their lowest common denominator, which it looks like it's going to be the same as above. It's also going to be 6. So again, I'm going to times everything that I need to respectively to turn that denominator into 6. So for fraction 1, I'm timesing it by 2. For fraction number 2 in the middle here, I'm going to times it by 6. And then for fraction 3, I'm going to times it by 3. And you'll see this will all make it the same bottom. So, okay, 2 times 2, that's going to be 4 over 6 minus 5 times 6, which is going to be 30 over 6. And then 7 times 3, that's going to be 21 over 6. Again, all the bottoms are the same, so now I can just combine the numerators together. You can let your calculator do the heavy lifting, but you will see that we end up simplifying to negative 5 over 6. Perfect. So now we're done simplifying the top and the bottom. This line here that's in between them is just implying that we are dividing. That line to say this over this just means you're going to divide the top by the bottom. So I'm going to rewrite this statement as saying the top, which we said was going to be negative 5 over 7. And I'm saying divide, and I'm using the little division symbol, by this bottom that we simplified, which was negative 5 over 6. Now in class, we talked about this rule of when you have fractions, or you have like a fraction in a fraction. If you are dividing fractions, which I'm going to do in pink here, we have a rule where when you're dividing, the way to approach this problem is that you're actually going to keep the first fraction the same, but now you're going to switch this from division to multiplication, and you're going to flip your second fraction. So bottom becomes top, top becomes bottom. So this is really going to be A over B times D over C. And that is how we divide fractions. So if you want to make a little note at this at the bottom, you can. And we're just going to apply this same rule to up here. So if I am keeping the first fraction the same, doesn't change, then I know that I need to switch this to multiplication, and I'm going to flip the fraction. So instead of negative 5 over 6, this is now going to be 6 over negative 5. Again, you could times top with top and bottom with bottom and then simplify from there. But I also kind of see from our little hack that we know from step 1 that if I've got the same number in the numerator and a denominator, I can cancel out. So because they're both negative 5, they're gone. So overall, we're just going to be left with 6 over 7. And we are done. And again, if you would have multiplied normally, you still would have simplified to 6 over 7. So that is your final answer. Then when we flipped to the next page, this is where we started talking about exponents, and we looked at like what are the components that make up this power function. We said that if we're looking at just the 3 here, which is in the bigger font, we consider that to be the base of our exponent. So that is the thing that is getting multiplied by itself a certain number of times. This 4, which is our exponent, that's telling us how many times we're going to multiply our base by itself. So for example, 3 to the power of 4 means I'm going to multiply 3 by itself 4 times. So this would be like 3 times 3 times 3 times 3. And then lastly, this whole cloud that this arrow is pointing to, it's just referring to it as a power. That's what we call it. So like we're saying 3 to the power of 4. That is the description. And there are some rules, especially when we're working with negative bases, because that will change our answer depending on the value of the exponent. So for example, we said if we've got a negative base and the exponent is an odd number, meaning it could be like 1, 3, 5, 7, 9, then our result overall is going to be a negative number. Versus if we've got a negative base, but our exponent is an even number, so that could be like 2, 4, 6, or 8, then we're going to have a final answer that is positive. And we're going to see this play out in the examples below. But our last rule is if we have a base that's negative, but there are no brackets surrounding this negative sign, then that means that our base is actually positive, but then we're just saying whatever our result is times by negative 1. So like the description says, you have to calculate that power first, and then we just make whatever our final answer is negative. So the overall result is going to be negative. So okay, let's put these rules to the test and let's see. So example 3, that's the first one there. We have to evaluate. Evaluate means tell me what this is equal to. So the 3 means I'm multiplying this by itself 3 times. So I'm doing negative 2 times negative 2 times negative 2. You could pop this into your calculator, or if you just did your 2 times tables, you would see that this is going to end up being negative 8. right? And why is it negative? Well, I've got a negative times a negative, which makes a positive, but this third negative means positive times a negative, which will overall give me a negative sign. Also, according to our rules up above that we just classified, we said if we've got a negative base and we've got an odd exponent, then we should end up with a negative result, right? Which does check out. You'll notice that the one right below it, which is kind of similar, it's still a base of -2, but it's to the power of 4. So now we've got an even exponent. So when I go to write this as repeated multiplication, and I'm writing this as -2 times -2 times -2 and times -2, you'll see, okay, if I do these two together, a negative times a negative makes a positive, and these two together, a negative times a negative also makes a positive. So overall, this is going to be equal to positive 16. This also satisfies the rules that we set up above, where we said even if we have a negative base, as long as we've got an even exponent, which we do here in this case, our overall answer is going to be even, or sorry, not even, positive. But in this case, it was also even. So positive. Okay. The last one was this special rule that we kind of like put on the end. And we said if there's no brackets, then we're saying that the base is positive, but then we're just attaching a negative sign at the end. So for example, if I really wanted to write this as repetitive multiplication, I'm saying just 2 is my base, not the negative. The negative is not attached to it. That's on the outside. It's almost like you can draw your brackets here to say it's just 2 to the power of 4 and then times -1 at the end. So this would look like in negative in repeated multiplication form, it'd look like negative sign and then 2 times 2 times 2 and times 2, which we know up above 2 to the power of 4 is 16, but in this case, because of the negative sign, we're going to have an overall negative number. So this is going to be -16. So you can see how having brackets versus not having brackets will change the sign of your final answer. The number will be the same, but the sign will be different. So in this case, we said the base is actually positive. It is +2, not -2. Right? But our overall answer is negative, and we said it's because of the negative sign in front of the base. So that's what we're filling in here. Because of the negative sign in front of the base. So I would say please be mindful when you're doing the practice problems and the homework to make sure that if your question has brackets, make sure you're inputting those brackets into your calculator. If it doesn't have brackets, then you don't need to, but those will definitely change your answer. So you want to make sure that you're being as accurate as possible. The last thing that we did together was looking at the exponent laws. So this was looking at when we're starting to multiply and divide things by the same base. And by base, we mean like if we're using a variable, like in these examples, a, or sometimes we'll even use a number as the base. So there were 3 laws that we look at. Some of them were introduced to you in grade 9, but just in case you forgot, there are 3. So there's the quotient rule, the product rule, and then the power of a power rule. The first one that you've got listed there is the product rule, and it says when you are multiplying things by the same base, you will add the exponents. So in this case, the base was a, and because they're both a base of a, I can just add their 2 exponents, n and m. Quotient is just the opposite, where they're saying if you are now dividing things that are the same base, then you're going to subtract the exponents, right? And the way they showed division was just in 2 different ways, of either using a division sign, which it looks like this division sign kind of cut out, like there should be a line there. So you could have it with the little division symbol, or you could have it stacked as like a fraction. That also implies division. And then the last one was power of a power rule. And that just means when you have an exponent to another exponent, like it's demonstrated here, where you could have, for example, I don't know, a squared and also cubed. When you have those two exponents beside each other, it is implying that you're going to multiply them together. So when we go into evaluating and we see numbers that are super big like this, if you go to plug that into your calculator, you're going to get an enormous answer. You're going to get an answer that might not even fit on the entire screen of your calculator. So this is where exponent laws kind of come into play to make our lives a little easier. So for example, I see that I've got some division happening there. So I want to deal with that first. So we're saying 3 squared times, and now because we're dividing these two things, I'm going to subtract the exponents. So we're going to be left with 3 to the power of 1210 minus 1207, which when you go to simplify that into a calculator, you're really going to only notice that this difference is by 3. So that simplifies, and that's a way nicer number to work with. If I continue over here, I'm just now saying, okay, I'm multiplying these two things. They're both a base of 3, so now I can add their exponents. So this will really be 3 to the power of 2 over 3, which simplifies to 3 to the power of 5. I'm not done here, only because this question does say to evaluate. And evaluate means tell me what this is equal to. So I have to state, what is 3 to the power of 5 equal to? Which in this case, it is going to be equal to 243. So that should be my final answer. With example B, you could like pause the video here, try it, see if you can get it. I'm going to work along as well, so I'll see if I get the same thing as you. But okay, I see, for example, this happening first. I've got a power to a power. I should probably address that first, and according to power of a power rule, it says that I need to multiply those exponents. So this first term is really going to turn into 5 to the power of 4 times 2. And the rest I will leave to be the same for now. Which 4 times 2, that's going to give me 5 to the power of 8. And again, I'm leaving these terms the same for now, because now I'm going to decide what my next move is. Which it looks like I'm doing multiplication first. So I'm going to add those exponents since they're both a base of 5. So this is really going to be 5 to the power of 8 plus 6. Which can be simplified. I can add 8 and 6 together, which would give me 14. So we see that I'm going to be left with 5 to the power of 14 divided by 5 to the power of 12. Again, these are huge numbers. Might not all fit in your calculator, so rather than evaluating what those numbers are, the fact that they're both a base of 5 and we're dividing, we're going to just subtract the exponents. So if I subtract the exponents and do 14 minus 12, you'll notice that the difference is just 2. That is way easier to evaluate and plug into your calculator than the stuff from up above, which 5 squared is really just 25. So this is where exponent laws really come in handy, because it's not wrong to evaluate them as they are. Like if you had plugged in 5 to the power of 12 or 5 to the power of 6 and then use those numbers in your expression, it's not wrong. It's just, it's going to take a long time and it's going to be stressful, especially as the exponents get bigger. That means the answers are going to get bigger. And again, it might not even fit on your calculator screen. So this is why exponent laws are so much more worth it, essentially. The last one was kind of a mix where we had variables, we had numbers, and we've got a mix of the rules where it looks like we're multiplying, we're dividing, and we've got the power of a power rule. So again, I'm going to treat this one like we did with the example on the first page, where when I've got a complicated looking fraction, my goal should be to simplify the numerator, simplify the denominator, and then go into applying my rules, or simplifying even further than that. So okay, if I'm just looking at the top, I am going to be combining coefficients with coefficients. So example, negative 2 times 8. I can even write this as negative 2 and times 8. So my coefficients go together. Then if I use a different color for my A's, I know that, okay, I'm multiplying and these things are the same base. They're both an A. So according to product rule, this is stating that I can add the exponents. So I'm going to do 3 plus 2. And then lastly, my B's, which again, they're the same base. We're multiplying, so I'm going to add those exponents. Now for the bottom, this square on the outside, we know that's going to correspond to power of a power rule. So I know my things with, for example, variables with exponents like A and B, I'm going to be multiplying those exponents together. But we cannot forget that this 2 also applies to the 4. So it applies to everything in the brackets. So this is like me saying 4 squared and then A to the power of 1 times 2, which is still just going to be 2. And then same thing, B to the power of 3 times 2. I'll even say with A, why it's 1 times 2 is if we do not see an exponent attached, we can automatically just assume that it's a 1, right? It's like an imaginary 1. It's just like how we don't say 1x, we just say x. So it's kind of like an invisible one there. Okay, if I get into simplifying, I know that negative 2 times 8 is negative 16. I know that my A exponent in the numerator is going to simplify to 5. And B is going to simplify to 7. And then if I do the same thing in the bottom, 4 squared, that's also going to give me 16. A, the exponent will be 1 times 2, which is just 2. And then B, the bottom will be 3 times 2, so 6. This is where now I can get into my division of where if I'm doing division with variables that are the same base, so like A with A and B with B, we're subtracting their exponents now. So I'm going to just draw a little arrow to continue on here. My first thing is my coefficients. I got negative 16 divided by 16, which anytime you're dividing something by itself, it's just 1. In this case, because I have a negative version dividing by a positive version of itself, my overall answer will be negative 1. And I'm going to just write the 1 for now. With my A's, we are going to subtract the top from the bottom. And same thing with B's. We're going to do top minus bottom. Again, I don't really need to write the 1, so I'm just going to put a minus sign overall. My A's, the exponent will simplify to 3. And for my B, this will just simplify to 1, which again, I don't need to write the 1 here. I can just write it as B. So final answer is going to be negative A cubed B. And we're done. So that was the end. Yeah, this is just a repeated page. So check over these problems, make sure you're confident with these things. With BEDMAS and exponent laws, the steps are so small and they seem so simple, but it's so easy to just make one little error or one little mistake or go out of order in BEDMAS and then your whole answer changes. So take your time with these types of questions, double check your answers with a calculator. Don't always have to rely on mental math. It's good, but in especially test scenarios, always good to triple check your work. So try those practice problems and I will see you in class.